AIOS, LLM Agent Operating System. Abstract. The integration and deployment of large language model, LLM-based intelligent agents have been fraught with challenges that compromise their efficiency and efficacy. Among these issues are suboptimal scheduling and resource allocation of agent requests over the LLM, the difficulties in maintaining context during interactions between agent and LLM, and the complexities inherent in integrating heterogeneous agents with different capabilities and specializations. The rapid increase of agent quantity and complexity further exacerbates these issues, often leading to bottlenecks and suboptimal utilization of resources. Inspired by these challenges, this paper presents AIOS, an LLM agent operating system, which embeds large language model into operating systems, OS, as the brain of the OS, enabling an operating system with soul, an important step towards AGI. Specifically, AIOS is designed to optimize resource allocation, facilitate context switch across agents, enable concurrent execution of agents, provide tool service for agents, and maintain access control for agents. We present the architecture of such an operating system, outline the core challenges it aims to resolve, and provide the basic design and implementation of the AIOS. Our experiments on concurrent execution of multiple agents demonstrate the reliability and efficiency of our AIOS modules. Through this, we aim to not only improve the performance and efficiency of LLM agents, but also to pioneer for better development and deployment of the AIOS ecosystem in the future. The project is open source at this link. One introduction. In the field of autonomous agents, research endeavors are directed towards systems that can operate independently, make decisions, and perform tasks with no or minimal human intervention. These agents are designed to understand instructions, process information, make decisions, and take action to achieve a state of autonomy. The advent of large language models, LLMs, has brought new possibilities to the agent development. Current LLMs have shown great power in understanding instructions, reasoning and solving problems, and interacting with human users as well as external environments. Built upon these powerful LLMs, emergent LLMs-based agents can present strong task fulfillment abilities in diverse environments, ranging from virtual assistants to more sophisticated systems involving complex and creative problem-solving, planning, and reasoning. One compelling example of how an LLM-based agent solves real-world tasks can be seen from Figure 1. Given the trip organization request from the user, the travel agent decomposes the task into executable steps. Then it follows the steps sequentially to book flights, reserve hotels, process payments, and update calendars based on the user's preferences. Figure 1, a motivating example of how an agent, that is, travel agent, requires both LLM-level and OS-level resources and functions to complete a task. During the plan execution, agents show the reasoning and decision-making abilities, which sets it apart from the traditional software applications that are constrained to a predefined set of functions or workflow. To realize this travel scenario, the agent needs to interact with both LLM services. For example, retrieving and understanding user preferences, deciding which tool API to call, generating reviews and responses, and traditional operating system services, for example, accessing disk driver and executing software. Accompanied by the exponential growth in the agent quantity and complexity, there is an increasing strain on the functionalities of LLM and OS. For example, scheduling and prioritizing agent requests in limited LLM resources poses a significant challenge. Moreover, the LLM's generation process can become time-intensive when dealing with lengthy contexts, occasionally resulting in the generation being suspended by the scheduler. This raises the problem of devising a mechanism to snapshot the LLM's current generation result, thereby enabling pause and resume behavior even when the LLM has not finalized the response generation for the current request. Furthermore, once an agent has obtained the list of available calling tools, determining the optimal sequence for invoking these tools presents yet another challenge, since multiple agents may need to call the same tool. Additionally, the concurrent operation of multiple agents necessitates a robust system for memory management across different agents, while also ensuring stringent enforcement of privacy and access control measures. To address the above-mentioned challenges, we propose AIOS, an LLM agent operating system to provide module isolation and aggregations of LLM and OS functionalities. To address the potential conflicts arising between tasks associated with LLM and those unrelated to LLM, we propose the design of an LLM-specific kernel. This kernel segregates the OS-like duties, particularly those related to the oversight of LLM agents, their corresponding resources, and development toolkits. Through this segregation, the LLM kernel aims to enhance the management and coordination of LLM-related activities. Within the proposed LLM kernel, we have devised a suite of modules, each dedicated to addressing the distinct functions pertinent to LLM operations. An overview of these modules and their respective functionalities is presented in the following, with the comprehensive discussion of their underlying mechanisms detailed in Section 4. Agent Scheduler prioritizes and schedules agent requests to optimize LLM utilization. Context Manager supports snapshot and restore the intermediate generation status in LLM and context window management of LLM. Memory Manager provides short-term memory for each agent's interaction logs. Storage Manager persists agent interaction logs to long-term storage for future retrieval. Tool Manager manages agents' calling of external API tools, for example, search, scientific computing. Access Manager enforces privacy and access control policies between agents. Aside from the modules, the kernel exposes an LLM system call interface through which agents can transparently leverage these services. Moreover, we designed the AIOS SDK to further encapsulate the LLM system calls, providing more convenient agent library functions for agent developers. With the AIOS architecture, an agent like the travel planner can break down its task into steps that fluidly combine LLM reasoning, for example, plan generation and tool calling decision, and OS-level actions, for example, accessing storage and executing software services. This synergistic combination of capabilities equips multiple LLM agents to tackle increasingly complex multimodal tasks that require reasoning, execution, and interaction with the physical world. Looking ahead, we envision extending the AIOS to support even tighter agent world integration, for example, through robotic control, more intelligent resource management, and safer multi-agent collaboration. Ultimately, AIOS serves as the crucial platform to facilitate the development, deployment, and usage of various complex LLM agents. 2. Related work. 2.1. Evolution of operating systems. The evolution of operating systems has unfolded in a progressive way, evolving from rudimentary systems to the complex and interactive operating systems of today. Initially, operating systems served to bridge the gap between the user-level tasks and the binary functionality of computer hardware, such as electron and gate manipulation. Their evolution saw a transition from simple batch job processing to more advanced process management techniques like time-sharing and multitask processing, which facilitated the handling of increasingly complex tasks. The progress moved toward modularization within the operating systems, delineating specific responsibilities such as process scheduling, memory management, and file system management, enhancing efficiency and manageability. The further advent of graphical user interfaces, for example Macintosh, Windows, and GNOME, makes operating systems more interactive and user-centric. Meanwhile, the operating system ecosystem has also expanded, offering a comprehensive suite of developer tools, providing runtime libraries. These tools enable application developers to design, implement, and run their applications efficiently within the operating system environment. Notable examples of operating system ecosystems include Android Studio, Xcode, and Cloud SDK. In these ecosystems, the operating system provides numerous resources to facilitate software development and serves as a platform for deploying and hosting software applications, leading to a thriving operating system application ecosystem. Nowadays, we stand at the transformative phase to see the potential of intelligent operating systems. With the incorporation of large language models, these advanced systems promise to further narrow the communication gap between humans and machines, forwarding a new era of user-computer interaction. 2.2 Large Language Model Agents. Large language model-based autonomous agents take natural language instructions as input for complex task solving. The research on large language model-based agents can be generally classified into single-agent systems and multi-agent systems. Large language model-based single-agent systems. Large language model-based single-agent systems use a single large language model agent for complex task solving, such as travel planning, personalized recommendation, and artistic design. The agent takes natural language instructions from users as input and decomposes the task into a multi-step plan for task solving, where each step may call external tools to be completed, such as collecting information, executing specialized models, or interacting with the external world. Single-agent applications may engage with either digital environment or physical environment or both, depending on the task to solve. For example, agents in virtual or digital environment may invoke APIs, browse websites, or execute codes, while agents in the physical environment may manipulate objects, carry out lab experiments, or make actionable decisions. Large language model-based multi-agent systems. Large language model-based multi-agent systems leverage the interaction among multiple agents for problem solving. The relationship among the multiple agents could be cooperative, competitive, or a mixture of cooperation and competition. In cooperative multi-agent systems, each agent takes and assesses the information provided by other agents, thereby working together to solve complex tasks such as role-playing, social simulation, and software development. In competitive multi-agent systems, agents may debate, negotiate, and compete with each other in a game environment to achieve their goals, such as improving negotiation skills and debating about the correct answer. Some multi-agent systems may exhibit both cooperation and competition among agents. Figure 2. An overview of the AIOS architecture. For example, War Agent models each country as an LLM-based agent to study how the interaction between countries can lead to international conflicts, where countries may cooperate with each other, such as establishing alliances and making peace agreements, or compete with each other, such as arms race, mobilization, and declaring wars. 3 AIOS layers. As depicted in Figure 2, the architecture of our AIOS is organized into 3 distinct layers: the application layer, the kernel layer, and the hardware layer. This layered architecture ensures a clear delineation of responsibilities across the system. Each higher layer abstracts the complexities of the layers below it, facilitating interaction through interfaces or specific modules, thereby enhancing modularity and simplifying system interactions across different layers. Application layer. At the application layer, agent applications such as Travel Agent or Math Agent are developed and deployed. In this layer, AIOS provides the AIOS SDK with a higher abstraction of system calls that simplifies the development process for agent developers. This SDK allows for the development of agent applications by offering a rich toolkit that abstract away the complexities of lower-level system functions. This enables developers to dedicate their focus to the essential logic and capabilities of their agents, facilitating a more efficient development process. Kernel layer. The kernel layer is divided into 2 primary components, the OS kernel and the LLM kernel, each serving the unique requirements of non-LLM and LLM-specific operations respectively. This distinction allows the LLM kernel to focus on LLM-specific tasks such as context management and agent scheduling, which are essential for handling LLM-related activities and are not typically within the purview of standard OS kernel functions. Our work primarily concentrates on enhancing the LLM kernel without making significant alterations to the existing OS kernel structure. The LLM kernel is equipped with several key modules, including the LLM System Call Interface, Agent Scheduler, Context Manager, Memory Manager, Storage Manager, Tool Manager, and Access Manager. These components are designed to address the diverse execution needs of agent applications, ensuring efficient management and execution within the AIOS framework. The specifics of these modules will be further detailed in Section 4. Hardware layer. The hardware layer comprises the physical components of the system, including the CPU, GPU, memory, disk, and peripheral devices. It is crucial to note that the LLM kernel's system calls cannot directly interact with the hardware. Instead, these calls interface with the OS's system calls, which in turn manage the hardware resources. This indirect interaction ensures a layer of abstraction and security, allowing the LLM kernel to leverage hardware capabilities without requiring direct hardware management, thus maintaining the system's integrity and efficiency. 4. AIOS implementation. In this section, we begin with an overview of the fundamental design and implementation of each module within the LLM kernel. Subsequently, we present the LLM system calls, which encompass essential functions for each module. At last, we discuss the exploration of the AIOS SDK, aiming to facilitate the development process for agent developers. 4.1 Agent Scheduler. Agent Scheduler is designed to manage the agent requests in an efficient way. Consider the various agents, denoted as A, B, and C, each of which has several execution steps. In the sequential execution paradigm, the agent tasks are processed in a linear order, where steps from the same agent will be processed first. This can lead to potential increased waiting times for tasks queued later in the sequence. The agent scheduler employs strategies such as first in, first out, round robin, and other scheduling algorithms to optimize this process. Through concurrent execution, the scheduler significantly balances waiting time and turnaround time of each agent, as tasks from different agents are interleaved and executed in parallel. This concurrent approach is visualized through a timeline where tasks from different agents are processed in an interleaved manner, ensuring that no single agent monopolizes the processing resources and that idle times are minimized. Apart from implementing the traditional scheduling algorithms, more complex scheduling algorithms considering the dependency relationships between agent requests can also be incorporated, which can be considered in the future. Figure 3, an illustration of the agent scheduler. 4.2 Context Manager. Figure 4, Context Snapshot and Restoration, where we use beam search, beam width equals 1, as an example search algorithm to illustrate this generative decoding process. The Context Manager is responsible for managing the context provided to LLM and the generation process given certain context. It primarily involves two crucial functions: context snapshot and restoration, and context window management. Context snapshot and restoration. Consider that the scheduler algorithms may involve time quantum operations, e.g., round robin, and agent requests may be suspended by the scheduler. This suspension happens even if the response has not been fully generated yet by the LLM. Therefore, it necessitates a mechanism to preserve the state of the LLM's generation process, ensuring that it can be accurately resumed once resources are available again. AIOS provides the snapshot and restoration mechanisms in the Context Manager to address this issue, which can be seen from Figure 4. We use the beam search process, a typical practice in LLMs, to illustrate the generative decoding process. For simplicity of illustration, we set beam width as 1. Specifically, consider the agent request as: determine whether there will be a rain in the destination of flight UA057. At each step, the LLM evaluates multiple potential candidates, with the most promising paths kept for further expansion based on the predefined beam width. When such generation process has been suspended by the scheduler at an intermediate step, the Context Manager uses the snapshot function to capture and store the current state of the LLM's beam search tree, including all intermediate probabilities and paths being explored for generating the response. Upon resumption, the restoration function is employed to reload the saved state from the snapshot, allowing the LLM to continue its generation process exactly from the point of suspension to reach the final answer: search weather in Paris. In this way, the Context Manager ensures that the temporary suspension of one agent's request does not lead to a loss of progress, thereby optimizing resource use without compromising the accuracy and efficiency of response generation. Context window management. To address challenges posed by long contexts that surpass the context window limit of LLMs, Context Manager also needs to manage potential expansion of context window. Specifically, Context Manager in AIOS supports basic text summarization and incorporates other expansion techniques to manage the context window. In this way, it can help enhance the LLM's ability to process and understand extensive contexts without compromising the integrity or relevance of the information. Memory Manager. As shown in Figure 5, Memory Manager manages short-term memory within an agent's lifecycle, ensuring that data is stored and accessible only while the agent is active, either waiting for execution or during runtime. The current AIOS supports storing each agent's memory independently, each of which other agents have no direct access to, unless it is authorized by the Access Manager. More complicated memory mechanisms such as shared memory pools among agents or hierarchical caches can be considered and integrated into AIOS in the future. Compared with the storage manager introduced in the following, the memory manager enables rapid data retrieval and processing, facilitating swift responses to user queries and interactions without overburdening the storage of AIOS. 4.4 Storage Manager. In contrast, the storage manager is responsible for the long-term preservation of data, overseeing the storage of information that needs to be retained indefinitely beyond the active lifespan of any single agent. This permanent storage in AIOS is achieved through a variety of durable mediums such as local files, databases, or cloud-based solutions, ensuring data integrity and availability for future reference or analysis. The storage manager supports retrieval augmentation 61. Through storing user preferences and maintaining historical interaction logs, the storage manager can enrich the agent knowledge update and enhancing the long-term user experience. Table 1. Manage tools in AIOS. The last column shows each tool's required input and output format. Category search. Tool name, Google Search. Description, search information by Google API. Input goes to image or text. Output goes to image or text. Category search. Tool name, Bing Search. Description, search information by Bing API. Input goes to image or text. Output goes to image or text. Category, computation. Tool name, Currency Converter. Description, currency converting. Input goes to text. Output goes to text. Category, computation. Tool name, Wolfram Alpha. Description, mathematical computation. Input goes to image or text. Output goes to text. Category, database query. Tool name, SQL query. Description, query data from SQL database. Input goes to text. Output goes to text. Category, database query. Tool name, Wikipedia query. Description, query data from Wikipedia database. Input goes to text. Output goes to text. Category, database query. Tool name, Archive search. Description, query articles from Archive. Input goes to text. Output goes to text. Category, database query. Tool name, Words API. Description, query definitions and synonyms of English words. Input goes to text. Output goes to text. Category, database query. Tool name, Urban Dictionary. Description, query random words, the current word of the day. Input goes to text. Output goes to text. Category, image processing. Tool name, Image denoising. Description, denoise images with noise. Input goes to image. Output goes to text. Category, image processing. Tool name, Image deblurring. Description, deblur images. Input goes to text. Output goes to text. Category, image processing. Tool name, Image classification. Description, classify images. Input goes to image. Output goes to text. Category, image processing. Tool name, Object detection. Description, detect objects and images. Input goes to image. Output goes to text. Category, image processing. Tool name, FaceRect. Description, detect faces and images by FaceRect API. Input goes to image. Output goes to text. Section 4.5, Tool Manager. The Tool Manager in the AIOS system manages a diverse array of API tools that enhance the functionality of LLMs. The Tool Manager integrates commonly used tools from various sources and classifies them into different categories covering web search, scientific computing, database retrieval, image processing, and more. In this way, the managed tools can cover different modalities of input and output, facilitating agent development within the AIOS ecosystem. Table 2. Instances of LLM system calls. Category, Agent syscall. Name, getAid. Description, getID of an agent. Arguments included, int_aid. Category, Agent syscall. Name, setAid. Description, setID of an agent. Arguments included, int_aid. Category, Agent syscall. Name, getStatus. Description, getStatus of an agent. Arguments included, int_aid. Category, Agent syscall. Name, setStatus. Description, setStatus of an agent. Arguments included, int_aid, string_status. Category, Agent syscall. Name, getPriority. Description, getPriority of an agent. Arguments included, int_aid. Category, Agent syscall. Name, setPriority. Description, setPriority of an agent. Arguments included, int_aid, int_priority. Category, Agent syscall. Name, suspend_agent. Description, suspend an agent's operation. Arguments included, int_aid. Category, Agent syscall. Name, resume agent. Description, resume an agent's operation. Arguments included, int_aid. Category, context syscall. Name, gen_snapshot. Description, snapshot intermediate LLM generation status. Category, context syscall. Name, gen_restore. Description, restore intermediate LLM generation status. Category, context syscall. Name, get_context. Description, get_context window length. Category, context syscall. Name, XP context. Description, expand context window length. Category, context syscall. Name, text. Description, clear current context, window. Category, context syscall. Name, set context. Description, set a specific context window. Arguments included context C. Category, memory syscall. Name, mem write. Description, write the interaction record into memory. Arguments included int aid, memory m. Category, memory syscall. Name, mem read. Description, read the interaction record from memory. Arguments included int aid, memory m. Category, memory syscall. Name, mem clear. Description, clear specific memory record. Arguments included int aid, memory m. Category, memory syscall. Name, mem alloc. Description, allocate memory for an agent. Arguments included int aid, size s. Category, storage syscall. Name, stow write. Description, write the interaction record into storage. Arguments included int aid, storage s. Category, storage syscall. Name, stow read. Description, load the interaction record from storage. Arguments included int aid, storage s. Category, storage syscall. Name, stow delete. Delete the interaction record from storage. Arguments included int aid, storage s. Category, storage syscall. Name, sto alloc. Description, allocate storage for an agent. Arguments included int aid, size s. Section 4.6 Access Manager. The Access Manager orchestrates access control operations among distinct agents by administering a dedicated privilege group for each agent. Those agents excluded from an agent's privilege group are denied access to its resources, such as the interaction history. To further enhance system transparency, the Access Manager compiles and maintains auditing logs. These logs capture detailed information about access requests, agent activities, and any modifications to the access control parameters, which help to safeguard against potential privilege attacks. 4.7 LLM System Call. LLM System Call interface within the LLM kernel is designed to offer basic LLM call operation functions. This interface acts as a bridge between complex agent requests and the execution of different kernels modules. As is shown in Table 2, analogous to OS system calls, LLM system calls offers a suite of basic functions that span across the kernel's modules, including agent management, context handling, memory and storage operations, and access control. The LLM system call list can be further expanded in the future to support more operations. 4.8 AIOS SDK. The AIOS SDK is designed to equip developers with a versatile toolkit for crafting sophisticated agent applications within the AIOS. This SDK encompasses a broad spectrum of functionalities, from initializing agents and managing agent lifecycles to facilitating complex operations like resource monitoring and generation plan for an agent task. Like any operating system, enriching the SDK to be comprehensive and developer-friendly is a long-term and never-ending endeavor. The current SDK functions supported in AIOS are shown in Table 3, which will be continuously updated and expanded to fulfill the needs of evolving agent applications. This development effort aims to provide developers with the tools they need to harness the full potential of their agent applications within the AIOS framework. Table 3, the list of SDK functions in AIOS SDK. Initialize agent, set up environment for agent execution, including resource allocation, void. Register agent, register a new agent to the system, providing it with ID and permissions, Boolean. Queue for execution, enqueue the agent for execution, void. Generate plan, generate a plan of a given agent task, object. Terminate agent, terminate an agent with cleanup, void. Create agent snapshot, create a snapshot of the agent's current state for rollback, object. Rollback agent state, rollback the agent state to a previous snapshot, void. Update agent config, update the configuration settings for an agent, Boolean. Authenticate agent, authenticate an agent's credentials before execution, Boolean. Track resource usage, track and report the usage of system resources by agents, object. Log event, provide logging of agent-specific events for debugging and auditing, void. List active agents, list all currently active agents within the system, list. Query agent history, query the historical operations of an agent, object. Encrypt data, encrypt sensitive data generated by an agent, object. Decrypt data, decrypt sensitive data for an agent's consumption, object. 5. Evaluation. In this section, we evaluate both the correctness and the performance of AIOS modules when multiple agents are running in parallel in AIOS. Our investigation is guided by two research questions. Firstly, whether the LLM responses to agent requests are consistent after agent suspension and transition to another agent, And secondly, how is the performance of AIOS scheduling in improving the balance of waiting and turnaround time relative to non-scheduled sequential execution? 5.1 Setup. Our experiments are conducted in Python 3.9 with PyTorch 2.1 and CUDA 11.8 on an Ubuntu 22.04 machine equipped with 8 NVIDIA RTX A5000 GPUs. We employ the publicly available LLMs for the evaluation. We configure 3 specialized agents: a math agent for solving mathematical challenges, a narrative agent for generating novel narratives, and a rec agent tasked with providing restaurant recommendations. Each agent is designed to send 2 to 3 requests to the backbone LLM during running. 5.2 Experimental Results. Consistency Analysis. To answer the consistency question, we first run each of the 3 constructed agents individually to generate results. Subsequently, we execute these agents in parallel, capturing their outputs at each step. To assess the consistency of outputs under the running of multiple agents in parallel and under the running of single agents one by one, we utilize the BLEU score and BERT score as evaluative metrics. Both metrics span from 0.0 to 1.0, with outputs produced in a single agent context serving as the reference standard, and we set the temperature parameter as 0 to eliminate the impact of randomness. As demonstrated in Table 4, BLEU and BERT scores all achieve the value of 1.0, indicating a perfect alignment between outputs generated in multi-agent and single-agent configurations. This result affirms the consistency of our design in effectively facilitating concurrent multi-agent operations. Table 4. Consistency of LLM-generated responses when running multiple agents in parallel, compared with LLM-generated responses when running a single agent one by one. Performance analysis. To answer the efficiency question, we conduct a comparative analysis between AIOS employing FIFO scheduling and a non-scheduled approach, wherein the aforementioned 3 agents run concurrently. In the non-scheduled setting, the 3 agents are executed following a predefined sequential order: math agent, narrative agent, and rec agent. We employ 2 metrics for assessing temporal efficiency: waiting time, the time interval from agent request submission to commencement, and turnaround time, the duration from agent request submission to completion. As each agent will send multiple requests to the LLM, the waiting time and turnaround time of each agent are calculated as the average of waiting time and turnaround time of all its sent requests, respectively. To mitigate randomness, we execute these 3 agents, both with and without scheduling, in 5 separate trials to report the results. As shown in Table 5, the non-scheduled approach exhibits prolonged waiting time for agents earlier in the sequence, but the effect is constrained to the specific agent, and turnaround time remains within the standard. Conversely, AIOS's scheduling mechanism efficiently regulates both waiting time and turnaround time, a benefit that becomes particularly evident for agent requests submitted later by agents, especially when LLM is large. This suggests the importance of our scheduling to accommodate parallel operations of multiple agents. Conclusions. This paper proposes the AIOS architecture, demonstrating the potential to facilitate the development and deployment of LLM-based agents, forming a more cohesive, effective, and efficient AIOS agent ecosystem. The insights and methodologies presented herein contribute to the ongoing discourse in both AI and AI system research, offering a viable solution to the integration challenges posed by the diverse landscape of AI agents. Diverse future work can be built upon this foundation, exploring innovative ways to refine and expand the AIOS architecture to meet the evolving needs of developing and deploying LLM agents. Future work. Beginning with AIOS, there are many directions for future research to pursue. This section outlines potential areas of study that expand upon the foundational features of AIOS. Advanced scheduling algorithms. The scheduling function of AIOS lays the groundwork for the development of more advanced algorithms. Future research could focus on algorithms that perform dependency analysis among agent requests, optimizing the allocation of computational resources. Additionally, some of the tool resources are locally deployed models, which can also be incorporated into the scheduling paradigm. This includes the management of tool status and snapshots, suggesting a move towards a unified scheduling framework that encompasses both agents and their tools. Efficiency of context management. more efficient mechanisms can be devised to assist context management. For example, the pursuit of time-efficient context management techniques could significantly augment user experience by expediting the processes of context snapshotting and restoration. Also, context compression techniques can also be leveraged prior to snapshotting, which can yield a more space-efficient solution. Optimization of memory and storage architecture. In the context of agent collaboration and communication, the future design of memory and storage systems can adopt a shared approach, enabling the sharing of memory and storage between agents. Such an architecture would enable agents to access a communal pool of memory and storage, thereby improving the agent's BOD decision-making ability, since one agent can benefit from other agents' memory or storage. Moreover, future work can explore hierarchical storage solutions designed to optimize data retrieval and storage efficiency. This could involve prioritizing quicker access and reduce storage allocation for frequently accessed data, and vice versa for less frequently accessed information. Safety and privacy enhancements. The aspect of safety in AIOS necessitates protective measures against various attacks, ensuring the system's resilience against malicious attacks, such as jailbreaking of LLM or unauthorized access of other agents' memory. In the realm of privacy, the exploration of advanced encryption techniques is vital for safeguarding data transmission within AIOS, thus maintaining the confidentiality of agent communications. Furthermore, the implementation of watermarking techniques could serve to protect the intellectual property of agent developers by embedding unique identifiers in outputs, facilitating the tracing of data lineage. In a nutshell, AIOS stands as a motivating body of work that brings a broad spectrum of research opportunities. Each outlined direction can not only build upon the foundational elements of AIOS, but also contribute to the advancement of the field at large. Acknowledgement. We thank Jian Zhang, Zhenting Wang, and Wenyu Hua for their valuable discussions and suggestions during the project. This concludes the reading of AIOS, LLM, Agent Operating System on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.